thank you for joining us today. Let me introduce myself. I'm Isabella Luppi. I study automation engineering, and this is my third year of my bachelor's degree. But tonight, I'm here speaking as secretary of the Automation Engineering Association. Again, I want to thank you all for joining us tonight at our new meeting on intelligent collaborative robotics. We really appreciate every single one of you who showed interest in what we do as an association.
So Isabella, do you want me to start recording?
Yes, please.
Okay, I will start now.
Okay. We want to thank you everyone who showed interest in our association and decided to subscribe to this event. I don't know if you know it, but our association is very, very new. We got together in September, but we only became fully official and recognized by the Italian state on March 4th, 2021. So it has just been a few weeks. Well, now I would like to let the president of our association speak very shortly, please, about us and what we do. So, Julio, you have the floor.
Thank you, Isabella. Good evening, everyone. My name is Julio Bakari, and I am the president of AEA. As Isabella said, we started building the association back in September with the idea to build a strong network of relationships capable to promote automation engineering, organizing events with expert speeches like tonight, company visits, workshops, and maybe also hackathons. Now, after 6 months, and despite the increased bureaucratic complexity caused by the pandemic situations, 2 weeks ago, we finally became an official association, and now we can start to work for you. So soon there will be the official event to launch the association and to present our projects. But if you're ready, would like to join us and help us building something new, please feel free to contact us on Telegram, Instagram, or LinkedIn. I will leave the link in chat soon. I hope you will find tonight's topic as compelling as we did. And given that, I would like to say thank you to Professor Rocco and Zanchettin for their availability.
Okay, thank you, Julio, for sharing these informations with us, and thank you for the professors for being here. And as Julio said, feel free, of course, to contact any of us if you need any further information or if you have questions or if you're just curious. So tonight we will have 2 rules you have to follow. The first one is please keep the microphones off during the entire presentation unless specified. Secondly, you can ask questions at the end of the presentation. You can either type your question or you can choose to ask your question through your microphone, but you have to ask for permission to speak. So please express your interest to speak in the chat and I will tell you when it's your turn to speak. Otherwise, just type your question and I will read it for you without any problem. I hope this clarifies everything. So without any further ado, let's get to the meeting. And please, Professor Rocco and Professor Zanchettin, you now have the floor.
Okay, thank you. Thank you very much. And thank you for this invitation. We are really excited, to talk to all the students. It's great, to have the Association of Automation Engineering. So I'm going now to share my screen. Okay, I hope you can see it. Okay, so presentation will be like this. I will start with the first part, then I will leave the floor to Professor Zanchettin. And since I am actually in the lab, close to the lab, maybe if we can do this from a technical point of view, I will try to also show something with the robot live. So the topic today is intelligent collaborative robotics at the MERLIN lab. And so let me see. Okay, so I will start this conversation with some figures on the automation, whether it is a risk or an opportunity. So this is in Italian, but it's clearly, understandable. So this is a study by the European House on Brosetti a few years ago, and they estimated that out of 21 million people occupied in Italy, there are almost 15% of them which are at risk. At risk of what? At risk of being substituted by automation. And the study also is very rich, I mean, in terms of information, and they broke down all the activities in several sectors, and specifically in the manufacturing industry, that is the part that is highlighted here. You can see that the higher the blue bar, the more people are working in this area, and of course, industrial manufacturing is the highest one, and about 20% of this large share of people that work, I mean, in this specific area are, so to say, exposed to a risk of being substituted by automation. In another study that was published a few years ago, very interesting, by McKinsey Global Institute, they made similar, I mean, consideration, and they tried to analyze all the working activities of people and try to classify them in terms of, to rank them in terms of risk of being substituted by automation. You can see that the activities that, I mean, undergo this risk higher, I mean, collect data, process data, and then predictable physical activity. What does it mean? Mean doing over and over the same activity. So if you work in collect data, process data, predictable physical activity, you need to be a little bit worried. So what is the conclusion? Will workers completely disappear for the factories? Are we going in some years to the model of the black light factory where only machine works and no human will be around? Well, this is not necessary. It's not necessary because, I mean, there are new paradigms, and one of these paradigms is when human and robot work together in a productive task. And this is exactly what we call today collaborative robotics, or collaborative automation, as we will also say. And is a new paradigm in industry, and we want today to explain to you what is this about, collaborative robotics, and how in the MERLIN lab we are studying it and what are our current research on this field. So if you take this chart where on one axis you get productivity and on the other axis you get flexibility, you can consider manual work at one of these extreme. The manual work is by far the most flexible. The human is the most flexible agent out of all the possible working agents, but unfortunately is not the most productive one. Actually, is the less productive one. On the other hand, you can have hard automation, so machines that are conceived to do only a certain kind of product, so they are highly productive but not particularly flexible. You can have industrial robotics as a first step to be a little bit more flexible, while maybe a little bit less productive. An industrial robot might be a little bit less fast, I mean, than a tailored automation plant. But in between, you can have this collaborative automation where actually the human and the robot once again work together to perform a certain task. And with this collaborative automation, you can get a good trade-off between flexibility and productivity. And I mean, the principle is this one. I mean, so suppose that you have activities that can be, in some sense, organized into activities that have low added value, and so they are easy and cheap to automate, so easy to do for a machine, and activity with high added value, or something like difficult or costly to automate. Think, for example, of activities that the robot is not yet so good at, like manipulating deformable objects, cables, and so on. So suppose that these activities, you have a completely manual process, but you want, to evolve from this, and you want to introduce a robot in your production and productive plant. And what you can do is that you can assign the activities with low added value to the robot, while to keep the activities with high added value to the human. And so get a team that get the best of the two agents. Okay, and you can do this safely, as we will see, without any infrastructure for safety. So the paradigm is actually an evolving one. You can have a different situation when it comes to cooperation, to interaction between human and robot. You can have just coexistence where human and robot do not actually share a same workspace. They both work, they each work on their own workspace, and occasionally the human has to to access the workspace of the robot, maybe to pick something or to actually give material to the robot to work on. Another paradigm might be synchronization, where you have the working spaces of the two agents might have a part in common where they actually can work both, but not simultaneously. So either the human or the work or the robot, work in this the shared workspace, but synchronizing each other. Cooperation is the most extreme, way of interacting between a human and robot, where they both share the same workspace and they can actually work together at the same task, with maybe also some physical interaction between the two agents. So this evolving paradigm can be seen in this picture, where you can see on the leftmost part the sporadic access, and in the middle one the frequent access, where the human and the robot work in different workspaces, but they have frequent interactions, and the persistent interaction on the rightmost clip, where you can see the human and the robot, in that case the Yumi robot by ABB, that we will see in other clips, that are working together in a production task, in that case, in particular to manufacture electrical circuits. Of course, when you have a machine and a human, you need to be careful about safety. And I will not, give you a lecture about safety. It's a topic, of university courses. I just wanted to give you a couple of examples on how we dealt with the safety in our research a few years ago. The first one is this. You can see that this is similar to the Yumi robot. Actually, is a predecessor of the Yumi robot. Was called Frida. It was a prototype from ABB, and we worked with ABB corporate research at the time, more or less 10 years ago or 8 years ago. In this experiment, you can see that there is this sensor that has been made by students, and it is formed by a shell made with 3D printing, on which there are some distance sensor. And you can see that the robot is aware of the fact that a human is around and keeps doing its production process, although the human is there. And technically speaking, it uses its redundancy and to actually make evasive motion in the so-called null space of the task. So meaning that it actually enjoys all the richness, of its articulation. Okay, and that's a first way to cope with safety. So having a sensor that is mounted on the robot itself. Another paradigm is this one, where you have a robot that is doing a repetitive action, and then you will see a former student of ours that comes into the scene, and it is actually perceived by the device that is up here, that is a 3D camera, and the speed of the robot is modulated as a function of the distance between the human and the robot. This actually is completely compliant with one of the safety standards that is dictated by the ISO, the International Standard Organization for Safety, that is called the speed and separation monitoring, meaning that the speed of the robot must always be such that, it can come to the full stop depending on the distance perceived between the human and the robot. And this is the way, we can deal with safety, and this is a very, easy to transfer to a real, production facility. In both of these clips, we have seen that the human is more or less a disturbance for the robot. There is no interaction. It's just a coexistence of the human and the robot. You can do more, of course, with robots. And one thing that you can do is to help workers. Take a look at this video where you can see a worker that does an operation that is called priming on this bumper of a car, and you can think of this worker doing this over and over for his whole day shift. Of course, it is kind of challenging for the upper part, of his body in terms of exposure to musculoskeletal disorders. And the musculoskeletal disorder is one of the big headache, of people that run productive plants, and the costs related to musculoskeletal disorders are extremely relevant, and not go into the detail figures, but keep in mind that this is one of the most important problems to be solved. So, in order to have a more productive facility where humans are involved. So the idea that we had is, why can't we use robots to help humans? And how can we do this? We can do this by having the robot actually carry in that specific case the bumper of the car, in order for the human actually to do this operation without having to make big motion with the arm, and avoiding stress on the musculoskeletal apparatus. So the idea is quite simple. You have a camera that frames the human, and thanks to some study in ergonomics, we know that in order to do a certain task, the upper part of the human body has to be actually arranged in a certain way. So in case the reference posture of the human is different from the actual posture as perceived by a 3D camera, we use something that is so familiar with you automation engineering student, so feedback. So we use a feedback, and then we move the robot in such a way that it actually forces the human to get back, the reference posture. And that is exemplified in this video, where you can see that the robot moves the bumper in a way that the human does not have to move. You just have to make micro movements. Of the hand, and you can see this device with these 3 balls that are here just to facilitate the task to the vision system. And so the robot, you can see, moves the bumper. So of course it's a relative motion, and you can do the same operation without exposing the worker to these problems. We move now to a different, so let me stop a little bit this, to a different scenario. So the robot can be a good helper to the human, but when you want the robot to actually work alongside with the human in a production tasks, so the human does something and the robot does something else, you can think of this fact. I mean, of course, the human can see, understand what the robot is doing, but the vice versa is not true. So don't be fooled by these nice eyes. This robot does not see, does not understand what the human is doing. So to say, the communication is asymmetric. And take a look at what happens here. So this is a very repetitive task, you can see. And everything works fine. But here you can see that the worker has some problems and she slowed down. Synchronization is lost. What will happen then, we will never know, because the video now runs back again. So we will never know. There is clearly a fault in the synchronization. So what can we do to improve the situation? As I mentioned before, collaboration is kind of asymmetric. The human sees and understands what the robot is doing. On the other hand, the robot has no clue of the work of the human. So if we don't do anything more, the robot is a pre-programmed machine and it does what the programmer told the robot to do. Okay, is this point clear? So the idea that we have is whether artificial intelligence can help us improve the situation, and in particular artificial intelligence combined with vision and cognitive vision. The first problem that we faced was this. Suppose that the human can do several actions, so we have a discrete set of actions, and what we want to do is, thanks to some vision system, we want to infer the ongoing activity of the human. So we want to understand, out of a possible set of activities, which is the one the human is actually doing in this precise moment. And we do this by assigning probabilities to each action and updating the probability associated to each action. And that is nicely exemplified by this experiment that we did a few years ago, where we have a very simple task is to put the cover in the top on an empty box, of course, to close the box. And the human can either, go to the bin where you have the empty boxes, or to the other one where you have the tops. And depending on the action performed by the human, the robot is supposed to do the complementary action. Okay, and there is a vision system that is actually identified here. And the idea is that with the vision system, you can track the motion of the hand or of the wrist, actually position. And based on some consideration that I will not go here into mathematical details, the idea is that you have two goals, and you actually offline build the path that might bring, the hand from the current position to the goal 1 or to goal 2 position, and based on the current measurement, you can update what is the probability that the human is heading towards goal 1 or towards goal 2. And there's actually is shown in this video, where you can see maybe a little bit younger Professor Zanchettin, who is actually performed in this picture. You can see that the robot understood the action made by the human. In that case, the human actually was picking the empty box, and the robot picks the top, and vice versa. So the collaboration is so smooth, so natural, and thanks to the fact that the robot is understanding what the human is doing, because it actually is able to understand, out of the possible action, in that case only 2, what is the one that the human is doing. Just let me move one step further, then I will give the floor to Professor Zanchettin. So the next thing that you can do is this one. Okay, now I again, that the robot can understand the human. But one thing that might even improve the situation is when the human is actually aware of the cognitive activity of the robot, meaning that the human might be assured when the robot, when he or she feels that the robot has understood. And so we pushed this idea, and together with another group from the University of Siena, Italy, used as a vibrotactile ring that it was mounted on one finger of the operator, and this is like the smartwatch. So you get a vibration when something happens, and the something happens is when the is understood what is the current action of the human. And this is exemplified by this video, where you can see our PhD student, Costanza Messeri, that is performing this operation that is an assembly of a pen drive. And you will see in a moment that the ring, the vibrotactile ring, will vibrate, because, this means that the robot has understood the action that she was doing, and actually the robot complemented with the following action. And here again, the vibrotactile ring vibrated. So now we have a robot that can understand what the human is currently doing. The human, on the other hand, is aware of the fact that the robot understands what the human is doing. What can we do more? And I leave the floor to Professor Zanchettin to actually continue. I will interrupt my presentation. So just 1 second. I will have Professor Zanchettin to be is relatore. Okay.
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 Thank you,
Andrea.
Paolo.
Yeah.
Yeah. Let's start sharing the screen. Okay. So we are here. Okay. Can you see?
Yes, we can see it, Andrea. Yeah.
Okay. Thanks. So what you have seen so far is that a robot can actually infer what the human is doing, but the actions that we have seen were so limited in time that any other approaches or any other application is not doable with this kind of approach. So let's assume that we have a longer action, and we need to synchronize the motion or the activity of the robot with the one of the human at the end of this action. So just to introduce an example, you have an action lasting 2 minutes, and so during these 2 minutes, the robot can do whatever it is needed without taking care of the human. But you want to be very precise at the end of those 2 minutes, because the human at that specific time instant actually needs the robot to continue. So you want to predict exactly when this help provided by the robot will happen in the future, and so you want to estimate the overall duration of an action that is taking a bit longer than just a few seconds. So the thing that you can do is monitor all the actions that the human had performed until now, and collect statistics, for example. So sometimes it happened that the human took 1 minute and 50 seconds, and another time actually the human took 1 minute and 55 seconds. Then another time 2 minutes and 10 seconds, and you take the average. And so what you get is the average duration of an action. So now consider an ongoing action. And you know that, it took 1 minute to arrive to the current situation. So can you guess what is the remaining time? So that is the answer that we try to answer. The questions already that we try to answer in this work. And of course, the thing that you can do is subtracting from the average duration, the actual duration of the activity so far. So assuming that the average duration is 2 minutes, and then just 1 minute has been passed, so we guess that the remaining time is 1 minute more. But of course, let me introduce a parallel with another topic that might be familiar to you. Let's assume that we have to travel from Milan to Rome by car, and it took 4 hours, for example. I don't know, probably a bit more. Let's say 6 hours by car. So if I tell you that I've been traveling for 3 hours, can you guess the remaining time to get my final destination? You will say 3, right? But if I say that I'm stuck in, I don't know, 5 kilometers away from Milan after those 3 hours, because there was a huge traffic before that, can you still guess that I will reach my final destination in 3 hours? And I would say no. So what we did in this work is to consider how long the current activity has lasted, but also the percentage of progress in doing this, the corresponding job. And based on that, we were actually able to achieve a way better estimation of the overall duration of the activity, and so of the end of that activity, so to synchronize the robot with the human, and vice versa, of course. So what you see here is basically what I've been trying to explain with this example. So we have a template activity which is collected by previous run of the same task, and so we have just a fraction of it. And the duration here is 0.5 seconds, where the activity actually lasts 1 second, but clearly you can see that is less than the 50%. It's just the 25%. So I would say that this is just 1/4 of the overall duration. So the activity will last 1.5 seconds more, not just 0.5. So this is what we did, and this is basically one example of this. So what you see here on top is our guess duration is 32 seconds, 33 seconds. And this is the activity running. So we are monitoring these former students with a camera, and you can clearly identify that there are colored markers on the gloves. And here, that's already the remaining time. So it's 16, 15 seconds less. And here you see our prediction, which is the red one. So it's our prediction of the overall duration of this activity versus the real duration that we can only know at the end of the task, clearly. As you see that as soon as we are at 50% more or less of the execution time of the action, we are actually able to predict very well the overall duration, whilst the average base is highly inaccurate in this case, which is this blue one, which is the average of previous executions. So now we have this information saying how long this activity will last more. And the motivation why we started working on this is because at the end we want to synchronize the task of the human with the task of the robot. And so we developed another algorithm which is even at a higher level, that tries to predict not just the overall duration of the current activity, but also the duration of further activities that the human will perform. So as we started at the beginning, just classifying the activities. So assume that human is doing activity A, which is, I don't know, screwing. Then activity 1, which is screwing. Then activity 3, which is hammering. Then again activity 1, which is screwing again. So, and you see this string of symbols, which is 1, 3, 1, 2, 1 in our example here. And what you want to guess is the next one. So it's like having words, and you want to guess the next one according to your vocabulary. But instead here we have, instead of words, we have activities, which is our vocabulary, and we want to guess the next one. Well, based on some Gaussian-based algorithm, which is more or less related to model identification techniques. So we have a model, which is an average of previous probabilities to see an action. We are trying to guess the next one. And so, of course, we can compute distribution of probabilities of seeing action 1, a distribution of probability of seeing action 2, and so on. Everything with respect to time. So after all, we have a distribution saying how long we have to wait before seeing activity number 5, for example. And this can be useful information to be sent to the robot. So assume that activity number 4 in this example is the one that needs some synchronization between the human and the robot. So at current instant, we want to infer when activity 4 will show up again. And so we have this probability distribution with respect to time, saying that it is likely that activity 4 will show up again in 30 seconds. And now, when the robot has this information, well, this is actually translated into, okay, I can do my stuff, and I have 30 seconds to complete. Because after those 30 seconds, well, the human will, I will have to help the human. So that's the reasoning that the robot can do internally within the controller in order to schedule the corresponding activities. And this is exactly what we have done, and you see here in this demonstration. So you see that they can go in parallel, but at a certain point, the human is actually needing the robot, or vice versa. So this is where exactly they have to synchronize. So you see that our former student here actually put a box while the robot was putting this circuit board inside the box, and then they are doing something together in a collaborative manner. So that exactly was the thing that we want to predict. So we want to predict when exactly in time the human will put the box in the table in front of the robot. This is not happening right now, but we are continuously predicting when this activity, which is exactly this one, will show up. And the robot is actually able to reason on that and synchronize with the human accordingly. Then finally, what we did is something even more complicated. So it's a scheduling approach. Well, scheduling means what should I do now? What should I do next? And what should I do after next? And so on. So assume that the robot now has to select within a number of jobs that are actually in charge of the robot. So the robot can start job number 1, job number 2, job number 3, and so on. And we have collected a lot of information coming from the human. So the natural question is, which is the task or which is the job that is the most suitable to be executed now by the robot, within the one that are available, of course. So instead of just having some operational research algorithm that is somewhat optimizing for the job assignment to the robot, we try to bring the human inside. So we do some kind of scheduling for the robot activity that is somehow human-centric. So the human is governing the collaborative station, and the robot is adapting to the human. It's not the human that is a part of the system to be optimized. So the human is free to select whatever activities is the best to be executed, and the robot will adapt by observing the behavior of the human. That is something that we can call intelligent collaborative robotics, which is human-centric from this aspect. And this is exactly some technicalities that we optimize based on observation of the behavior of the human. I will skip that in favor of this video, which is probably more informative. So we see now a very complicated arrangement of one human and actually many robots. And here you see that there are two robots, but actually the robots are more than two. So there's a dual arm robot, and there are those two carts going back and forth. So they're not going back and forth randomly. We're just observing when the human needs to put something in the cart to ship that to the robot. And we coordinate the motion of those two carts as well as those two robots, depending on what the human is doing. And also the percentage of advancement and everything that we have seen so far. So you see that this is a very fluid cooperation between agents, but they're not all humans. So they can cooperate each other in a very fluid manner because the robots are actually aware of what the human is doing, and they are coordinating with respect to what the human is doing thanks to this intelligent or artificial intelligence layer that we have put in the middle between the human and the robot to allow the robots to understand humans. And you see that there are a lot of assembly tasks, including also some storing and packaging at the end of the line that is done with this big and orange robot. Last but not least, I would like to just mention what we are doing so far. So we're trying to mix what we know from traditional industrial automation. Well, traditional automation, I hope that you are aware of, is 100% more or less based on PLCs. And when you have a PLC, it means that you have signals coming from the field. And this register here is exemplifying the situation. So where, of course, green is true and red is false. And then you mix those signals with, thanks to Boolean expression, and the condition that you can get out from it can be used to decide whatever the robot should do with some control logics. That can be sent back to an industrial robot, for example. But assume that now the thing that you want to control is a collaborative station. So the one with the robot and a human operator working side by side and somehow coordinating with respect to each other. So there is something that we have to put here. So while it is evident that the robot can send signals, digital signals to the PLC, what kind of signals the human can send? Well, thanks to artificial intelligence, we can observe the scene and understand what's going on. So here we have a human that is tracked and monitored with a camera, for example. And here we can clearly recognize that there is an instrument or a tool that the human is using. So we have here an artificial intelligence layer that is containing all the so-called digital twins, so the internal models of the reality. And so this is the world model that we are keeping maintained. So in this case, what we have is that the artificial intelligence can say that the human operator is using an runner, which is this tool here. And this information is either true or false. So in this case, it's true according to the current information. And this Boolean or digital information can be sent back to the PLC level, let's say, allowing the robot to decide what to do next, for example, in the same scenario that we have seen before. So we are kind of mixing, from the right-hand side perspective, industrial automation, which is PLC-centered, with intelligent automation, which is powered by AI. And we think that this is the approach to better coordinate humans and robots at the shop floor. So here you see two examples. On the left, you see the robot that is actually disassembling a work part, and it is also coordinating with the human. So it is aware of what the human is doing, the percentage of advancement, also occupancy, as you can see. The robot was stopped along the path because the human was there. And then you see that again. And there are all those stuff that are mixed together in this demonstration. In this right-hand side demonstration that was taken from, I think, the last fair that we had. That was in October, November 2019. That was the Maker Faire in Rome. Well, the robot is monitoring what the human is doing, exactly using the same principles. And this is actually synchronizing the task with the human. So see, now that the robot is taking this work part, but it waits for the human to free the area before actually proceeding further. Well, I think that was the last slide before the final part of this presentation. This is actually the team. So you see here the two of us and all PhD students and researchers that are working in the lab. And of course, we have a lot of master students. I think that we are counting something like 50 presently active master students working in the lab. And so, of course, it would have been too much crowded to play soccer with 50 students. So we just put the 12 of us. So we have one more when we have one extra player in the field right now. So thank you very much. So and we'll leave the stage again to Professor Rocco.
Yeah, thank you, Andrea. So Zanchettin. And so now I will try to do something difficult. So I will try to switch to another device and try to give you a live view of the lab. So maybe Andrea, in the meanwhile, say something.
I think that we can open for a few questions if there are questions in the meanwhile. So I'm happy to answer if you have questions. Then we can stop the Q&A session just to show the lab, and then we can continue with the Q&A.
Yes, I agree.
Okay.
If somebody wants...
Can you see something, Andrea?
Yes, we can see the stairs. Okay, that's the live walk towards the lab. Okay, that's the lab.
That's the lab. I mean,
but we cannot really hear you, I think.
Now?
Okay, now it's better. Thanks.
Okay, sorry. So this is the so-called Leonardo Robotics Lab that actually puts together the air lab that is here, the near lab that the biomedical application of robotics, while the air lab is focused on artificial intelligence. And then all these are desks for students. For a student. Yep. And this is the MERLIN lab. This is the door. The first robot that you can see is the Camaro Robot here. This is a 6 degrees of freedom robot, for those of you who understand what does it mean. Now it is actually set up for a demo. Andrea, can you tell a little bit about this demo?
Yeah, it's more or less the evolution of what you have seen for the speed and separation monitoring. So it's basically all about safety. So there is, if you can rise a little bit the camera, there's a Kinect on top, which is there, on the left. Okay, you see there that there's this Kinect camera that is looking at the scene. And we are trying to further go on with the research regarding safety. So we want to maintain a separation distance between the human and the robot that is as big as the velocity of the robot is. So the closer the robot to the human, the slower the speed should be. So that's the key idea. And the demonstration is basically some logistics task, which is a palletization of boxes.
And with this robot, actually, we did also some other experiments that have nothing to do with the human-robot cooperation. For example, we recently made a project with Brembo to make the barring with force control of some of their calipers. And so that is the the newest robot. It's a collaborative robot. It is from a Doosan company. It's Korean or Chinese, I can't remember exactly, but it's
Korean.
Korean, yes, one of the best collaborative robots in the market. It has been installed last week, so it's brand new. And we will use it for some projects. I cannot go into details here because they're kind of confidential. Yeah, but it's up and running. Yeah. Now I can move to the collaborative robotics area. So that is a 6 degrees of freedom robot from ABB. It's called IFB 140. And it is used for several, we have used it for several experiments. And in this case, you have this handle. And for those of you who understand what does it mean, it also has a force sensor because it is used to make experiments on some advanced manual guidance of the robot. And here you can see the Yumi robot that from ABB, and I'm not sure now what is the experiment that it's supposed to do here, because it changes depending on the project. But anyway, this is the dual arm robot by ABB, and we use it particular together with that device. You can see it. It is called the Smart Robots, and it is a device that is actually produced and marketed by a company that is called, once again, Smart Robots. And that is a company that is a spin-off of this lab. And meaning that it was funded by myself and Zanchettin and an industrial partner a few years ago. Because I mean, that is a process that sometimes happens when there are some good ideas, I mean, in a research lab that are ready to be transferred to the market. Don't know if Andrea, you want to comment about that?
No, it just I can comment the demonstration that is running there. So you have seen this camera, smart robots, and what you see here is part of the setup that is used for this demonstration. So we are aiming at assembly some braking system for motorcycles, and this is part of the setup that is used for this purpose. So the human and the robot are actually cooperating, and thanks to the system. And the last thing that we have seen during the slide presentation, we are telling the robot what the human is doing. So it is screwing or it is using the nut runner, and the robot can adapt its workflow based on this information.
Okay, excellent. And last things are this universal robot. That is a collaborative robot, a very famous collaborative robot. And it is not actually owned by our lab. It is owned by a company that is called Camozzi. And maybe we can talk about this project later. And with Camozzi, we have a very ambitious project. We want to set up an entire production line mixed between a human and robots. And this robot is here, but is supposed to be in a new facility that the Camozzi company is preparing, not so distant from here. And this is more or less what we have. We also have an educational robot here from Camaro. It's called Ido. And an old kind of device that we built. It's a real manipulator that is made up by a quadcopter and a small robotic arm. That's it for the live presentation of the lab. So I will now go back to my laptop. So Andrea, if you want to start answering any questions.
Yeah, there is already one. So Isabella, please can let me know whether I can start answering questions.
Yes, if there's someone who wants to speak, you can just write it on the chat, and we'll let you speak.
Okay, and meanwhile, I can read and answer the first question from Giuseppe Longo. So are there any emergency procedures to preserve the human safety? And Giuseppe is thinking about situations in which collaborative arms have some faults and go against during human tasks. So, of course, there are norms and prescriptions that are, and there is one specifically for collaborative applications. So every robot that can work potentially with the human, and all the robots that you have seen in the lab, including the orange and the red one, which are something like that we can call industrial robots, are actually capable of working with the human. And some of those are also able to hit the human without transferring too much energy. And so those are the robots that we can call collaborative robots. So those that are lightweight, possibly covered by padding material and so on. So they can hit the human without actually hurting the human because they are so lightweight. The others can still work with human, but you have to preserve a certain distance. So this, you have to stop the robot before hitting the human. But in all the cases, those are collaborative applications. And collaborative barely means safety.
Yeah,
Okay, thank you. The next question, I believe, is for Professor Rocco. During the robotic course, we have seen with Professor Rocco that every robot has singularity points. How do these points affect the interaction between robots and humans?
There's nothing special with singularities when it comes to interaction with robots and humans. I mean, the robots has to be commanded. So I guess that you are students now in fundamental robotics, and so the robots have to be the motion of the robot has to be planned, and exactly the same problems that you have when you plan the motion of industrial robots might, I mean, are the same issues with a collaborative robot. So you need to be careful about singularities, otherwise the robot can stop. You need to avoid them, maybe moving in the joint space or staying away, I mean, from singularities. But I mean, there is no kind of, I mean, peculiarity, peculiar relation between singularities and human-robot interaction. Will the workers?
Yes. Yeah. Will the workers need an additional preparation in order to be able to work with these new kind of robots, or won't it be necessary?
That's a good question. Also, the previous one was. I can try, and maybe Professor Zanchettin can add. Well, it depends. I mean, if you, my opinion, if you are just, I mean, how can I say, a worker that is doing is simple work, and you have just the robot that is doing something with you, probably you do not need to understand much about robotics. It's just a device, and similar as you have a laptop, you have a screen, you have a printer, now you have something that moves and helps you. And that is the easiest way, I mean, to go for the worker. So you just have to adapt to the presence of this strange machine. Of course, if you want to do more and if you want to program the robot, you need to know something about programming robots. And that's basically what happens. Andrea, if you want to comment.
Yeah, there are a lot of possibilities, or there are a lot of possible answers to this question. So, for example, safety is also another possibility of interaction that the workers should be aware of. So they're typically trained, at least for safety purposes. So workers have to be aware of safety prescriptions, and they have to be aware of how to manipulate the robot, how to work with the robot. So they're not just there to work with, so they are trained also to work with the robot. And what we have shown in our research is that the more people are trained, the more fluid is the interaction. So people that are used to work with robots are of course, interacting in a more fluid manner.
Yeah.
Thank you. So in the 40-second experiment you shown before, the algorithm started predicting the final result around the 25% mark, 10 seconds. Is there a minimum amount of time where the data is enough to start predicting efficiently when the robot will start its task?
I think this is something that you commented, Andrea. So
yes, there's no enough time, but I would explain like this. If you start walking towards a certain position, then you have to understand the average pace that you have while walking. If you don't walk, there's no prediction that can happen because everything is basically a random number. We cannot infer where you will start walking. So there is a minimum number of data for an efficient prediction. After that, you can start predicting, and of course, the more data you have, the more effective the prediction. But there's definitely a lower bound in the amount. So the better the prediction you can implement, probably the better is the outcome. Also with few data, but of course, some data is in the end is necessary to have in order to start predicting. I hope that I have answered the question.
Okay, I don't know if you have private questions, because I only received the questions to everybody.
no, we do not have private question, but there is one question by Guido in the chat.
Okay. How much is collaborative robotics present in Italy? Is it a growing trend?
Well, I can comment a little bit on this. First of all, as my student, I don't know if all of you are my students, but so I always give some figures about the market of robotics, and Italy is the second market of robotics in Europe, with more or less 10,000 industrial robots sold per year. And collaborative robotics is kind of a niche still in the big market of industrial robotics, estimated to be 5%, but is estimated also to grow very quickly next year. So in Italy, I would say that collaborative robotics is more or less the same share of the big market of industrial robotics as abroad. There is a lot of interest in collaborative robotics, and one reason is that, as you know, the industrial, world, I mean, in Italy is made by, most of all, by small, medium enterprises, small, medium companies. And collaborative robotics is, of course, one very nice solution for this kind of companies for a lot of reasons that I will not now need to list. So collaborative robotics is a good, product for small, medium enterprises. So there is a lot of interest and also a lot of units that are sold per year. Do not have exact figures of how many collaborative robots are sold in Italy.
Okay, I have a question that arrived privately to me.
Okay.
I know that flexible robots are a hot trend in robotics. There are cobots too. It's two, and the research isn't enough today. I don't. Can you please retype the question?
I think that I have understood.
Yeah, we understood flexible robotics. Yeah.
Okay.
I mean, as I have understood correctly, what you mean by flexible mean that a robot that can bend. And in this sense, I would say that there are two parallel tracks. So, collaborative robots, so the ones that you have seen in the lab and also in other applications, are surely less rigid than industrial manipulators that are traditional heavy manipulators. But they're not flexible at all, so they cannot bend. So there is some flexibility, and that is helping for safety, but they are all very precise at the same level of an industrial robot or a traditional robot. So when you work with a robot that is meant to be applied in industry, you really want it to be fast and precise. So both fast and precise. So a flexible robot is typically a lightweight robot, which means that it is probably fast, but because of flexibility, it's not surely precise. And this is something that you don't want to have in factories. But there is a lot of room for flexible robotics in other fields. So nowadays, I would say that 60% of robots are within factories, and the 40% is outside factories. So if you look at medicine, healthcare, there's a lot of space for flexible robotics in this sense. So robots that can deform somehow.
I have a question privately. Maybe I can read it.
Yep.
If you agree, Isabella. Okay.
Yes.
With this new type of robots, for example, the ones with arms, need to have more human-like movements when they interact so closely with humans. Efficiency will still be the main focus. It's a very nice question, and we actually did a nice research on this back when Professor Zanchettin was a PhD student, actually, and so some years ago. And
a few years ago.
Yeah, of course. It was a brilliant research, and so we actually made this with reference to the Yumi robot, or better, the predecessor of the prototype 3D robot. We made this research. We actually, first of all, analyzed the motion of the human in doing some typical assembly task. And so to make a long story short, we discovered that there is a correlation between the position and orientation of the hand and this angle that actually, makes, the posture of the human arm. And this correlation was identified and was transferred to the Yumi, or by the 3D robot, that now has this kind of human-like motion. And we also made experiments with volunteers that were closer to the robot, moving either with non-human-like motion and with human-like motions. And we were able to conclude, using some physiological measure on the volunteers, that when the human is closer to a robot that moves with a human-like motion, the stress induced on the human was less. Even not at a cognitive level, but at an objective level, the stress was less. And that was a nice research. And of course, so the conclusion is that the more similar to the human motion are the robot motion, the best, is from, psychological point of view, the acceptance of the human, of the robot on the human side. Now there is a public question, maybe Professor Zanchettin can take it.
Yeah, for the image recognition part of the process, did you use an existing data set to train the model, or did you collect the data yourself? So we use both approaches. So we can collect data and then train our algorithms based on these data, or we can use data set that are publicly available. Those are the two options when we use machine learning algorithms or neural networks. But we are also using model-based techniques for image recognition. So in this case, we don't need any kind of data set. We just use the model, for example, for object recognition that we are currently developing. We assume that we have the model of the object that we want to recognize, where model means the CAD model.
And I have a private question.
Okay.
Is the MERLIN lab responsible for possible accident with robots that developed for partners companies?
Don't get very well the question, but all the robots are insured. So if we break a robot by a company, hopefully we will not have to pay. We will call the insurance company. I don't know if that was the question.
Yes. And Nicola asked, do you think that in the future all the robots could have a collaborative part, or there will still be a difference between collaborative robots and industrial robots?
Yeah, I think that, so collaborative robots are nice. So I would like to say a couple of things, then Zanchettin can comment. First of all, some interaction can be done with whatever robot, industrial robots. So there are some allowed ways of interacting with a robot that have manual guidance or speed and separation monitoring or control stop that can be done also with traditional industrial robots. So on one side, of course, you can do only limited things with dangerous industrial robots when the human is around. But industrial robots will, survive and will stay there because there are operations that that makes no sense to do together between the human and the robot. Think to some loading of very heavy parts or how can I say, welding or painting. So there is no need in such operation to have a direct cooperation between the human and the robot. And so in that case, industrial robots, I think that will have a long life.
And we have a question from Diego. Are there some researches about collaborative robotics in domotic field?
Yes, they're basically researching in every kind of application of robotics. And I think also I can answer the next question that is for medical or surgical application. So I think that you cannot mention one possible application where robotics is not somehow under investigation, at least. So there are in domotic, in the domotic field, but there are just research or prototype robots that are working in the domestic field, and I don't think there are commercial products unless you want to look at toys or I don't know, like the Aibo dog that was a toy, a robot that is going around. I think that the only robot that is really inside houses is the cleaning robot, so the Roomba or whatever, but I would not call it collaborative. It's just something that is going around on the floor. So there's no collaboration. The reason is that, believe it or not, a domestic environment is very dangerous. So just go to the kitchen and allow a robot to manipulate everything that it can get in the kitchen. It's very dangerous. It's even more dangerous than in a factory. So the domestic environment is so unstructured that putting there a robot will follow with a lot of risks for the human in terms of safety. And I would say that it's good direction to go with the research, but we're not surely not ready for this kind of domestic applications. And I can go today to the next questions, where surgical or medical applications. Well, this is indeed a nice field. It's probably more mature than domestic applications. There are indeed commercial surgical robots. One is a robot that we have in the lab. We didn't show it, but there's a surgical robot, which is the Da Vinci robot. And the group that is basically working next to our lab is indeed more focused on medical application and especially surgical applications that they do use collaborative robots, for example, to help the surgeon to deliver parts or to do some tasks. But of course, it's a research level. While teleoperated surgical robots is at commercial level, I would say. But the human is there, so the robot is it's not the correct term to call it a robot, because it's completely teleoperated. There's no autonomy in surgical robotics.
I think that we skipped the question by Christian. You think that in the future human beings... oh, sorry, this is a private one, so that is why you didn't see. So maybe I will read it. Do you think in the future human beings will finally work on concept, abstract ideas and non-manual labels, delegating them to the robot, or is it just an utopia? Is this more a technological, political, ethical limit? Well, I don't think that...
define future first.
What? Yeah, what is the future?
Define future is 10 years or 1,000 years.
In the future that we will live, I mean, of course, we have a different idea of future, myself and you, but in my future, for sure, no. I mean, we will still have the need for human workers, and for several reasons, because, I mean, automation is for several tasks, but not for all. There are some tasks that, I mean, it is economically not advisable to automate, because they change every time, for example, and they are difficult to be made by robot. And also we need to, also, of course, have a human to do something productive. So I don't know if this is an utopia to have a human sit down and think, and the machine do all the jobs. Maybe in a very remote future we will have this situation, but not, I mean, in the next future.
So I have a question about what we spoke before about possible accident with robots. What if something happens with humans, specifically in medical applications?
I can say it again.
If I can repeat it.
Yeah,
please.
So before we spoke about a possible accident with robots, what if something happens to a human with a robot in a medical application?
Okay. So that's actually the point why the only robot that can work in medical application on a human patient is not actually a robot, but it's teleoperated, which means that there's still the surgeon in the same room or in the other part of the globe that is operating the robot, and without the surgeon, the robot can do anything. And still there is the risk of some damage in the software and hardware architecture, but it's completely mitigated. So there are stronger regulations when you have to go on patients that do not allow you easily to build up a robot to be used in surgery. But there's still the situation that something can happen, and of course there's no application in a commercial that has zero risk. So also industrial robot has some risk of failure, but also surgical robots have some risk of failure, clearly lower, but surely not zero.
I have two questions. One is a little bit long. I can try to read it. How a collaborative robot understands when an operator does a wrong movement that would cause a wrong predictions? By only statistic data and probability results, or there is a limit on randomness which can cause a stop? Well, that's a tough question. So we do have ways, I mean, to understand when a human does something wrong. Not sure whether, I mean, whether you are referring to with the prediction of maybe what Zanchettin was saying about next action to come. Andrea, do you want to comment on this?
I mean, if you know exactly what the human is supposed to do, so you have some kind of receipt of what the human should do, not necessarily in one order, but you know that the human can do either A or B, but surely not C. And you have a model for C, then you can easily recognize when C happens and say that's the wrong action. And of course, there is also the risk for misclassification, which means that the robot is, the human is doing A, but you misclassify that being saying that it is C, and you rise an assumption. But of course, the human is there that can promptly correct the artificial intelligence or whatever you can, however you, whatever you can call it. And so still the human is there, so it can mitigate the problem of solving errors. So humans are excellent problem solvers. So for this reason, that there's of course the risk, but I wouldn't say it's so dramatically problematic.
There was another question that the student sent to me directly. So I go first. Question is, which microcontroller do you use to control those robots you showed? Well, we don't.
I would be nice if we could use a microcontroller, but it's a standard
microcontroller. Yeah, exactly. So please consider that we are working at a kind of higher level. So we are not, working on the, low level axis control. That is the one, of the robot manufacturers. You can see the way we work is to interface the robot with external sensor, process the information, and then somehow communicate the elaborated information to the robot. And in order to do so, we can just use external PCs. We do not need to use microcontrollers.
So I can read some private action questions also. So Leonardo is asking whether I think that in future there will be some robots that can operate directly on humans. Where operate, I think that you are mentioning surgical operations. That's the trend. So there is also with the autonomous car, there's the trend of increasing the level of autonomy. And you have autonomy, no autonomy, basically, which is more or less 10 years ago, 20 years ago, and then full autonomous car where you just sit down, you don't have even the wheel. And the same thing is happening for surgical robots. There's no autonomy at all, which is the standard situation where the robot is completely teleoperated. And there's in between, there's some shared autonomy, which means that the human is responsible for the main duties, but still the robot can decide not to operate because it is risky, for example, or to stop because to prevent errors from the surgeon. And of course, at the very extreme level, we have completely autonomous surgical robots, but that's still the future, and everything has to be first researched. Then we have to have norms. Then we have to have companies. And then we have to have a market and application. So it's a long way. So we do two more questions.
Yeah.
Yes. Can we consider active exoskeleton as cobots?
I would say no.
You will say no, but it depends on what you define as cobots, of course.
Well, if you look at the definition of a robot, it's something that can operate autonomously.
Yeah.
So I would not call a robot something that needs the human to operate. So a cobot does not need the human at all. So the human can be there to operate with the robot, but the robot is autonomous. An exoskeleton without the human, it's rather a humanoid robot, I would say. If it can operate autonomously, but without the human, it's not. I would not call it a robot.
Yeah, even though some people do call them robots, but strictly speaking, it's not a robot.
Yeah, according to the definition.
Yeah, sure.
And Gianluca asked, can already existing robots manipulators be reconfigured to work collaboratively with humans?
Maybe I can take this. And so once again, please consider that some of the interaction modes that are allowed by the standards that can be done with all industrial robots. So once again, the robot just stops, control stop, and hand guiding and modulating the robot depending on the distance. If you want an existing robot to be used exactly as a cobot, well, that's another story. And what happened actually is that some companies, some big players of robotics, came into the market of collaborative robots, and the first thing that they did was more or less what you are actually suggesting. So they took one of their commercial industrial robots and they kind of adapted it to be collaborative by covering it with some surfaces that were allowed to have a compatible interaction with a human. So some kind of elastic surface. And in that way, that could be certified as a cobot, also with some speed limitation. But in the second round, these same manufacturers actually put in the market collaborative robots, that were conceived directly in the design process as cobots. A question about software. Andrea, please take it.
Just a curiosity, what are the main softwares that are typically used to control this kind of robots? Thank you. There are a lot of software that can be used. So the robot has its own programming language. So you have to program something that the robot is supposed to receive with a Ethernet connection, for example, with the programming language of the robot. And each robot manufacturer has its own programming language. So the question is, should I be aware of or expert of all of these programming robots? Answer is no, because they are more or less the same. It's just changing the names of the functions or of the methods of the instructions. But they are more or less 100% the same. Just the names of functionalities are different, and everything that deals with the tools that you bring, that you build around the robot is your own choice. So we use C++ programming and MATLAB for prototyping. Some students are using Python. Everything that can communicate. Well, a good thing that having everything connected to the internet is that we can eventually connect all the nodes with some Ethernet connection. So it doesn't really care whether you have the same programming language. So it's just a matter of sending Ethernet messages, and that's it, I think.
Okay, from now on, we're not open for questions anymore. So we're just gonna answer the last questions. So I have a few questions privately that I'm going to sum up in one question. How can students join the lab, and what is your advice?
Well, how can students... So there is also a public question that is similar. So have you some advices to younger automation engineering students to start entering this? So I will start, and then Professor Zanchettin can complement as usual. So in terms of advice, of course, for you, the students, simple advice is to, if you can, if you want, in your study plan of the Master of Science, of course, try to pick some courses that deal with robotics. Maybe not too many, but of course, at least some of them, in order to have, a whole training on robotics stuff. And my advice that I always try to give to students is to try to start looking at what industry does. And that can be done today in a variety of ways. So take a look at the websites of companies, take a look at the magazines that magazines that for companies on automation. There are some of them, automation or robotics. You can read them, and they are intended for people that work in industry, which are exactly you in some years. So if you take a look at them in advance, you will be well prepared. In terms of accessing the lab, that is a little bit difficult question because, of course, the lab is a research lab, it's not a teaching lab. We do not make practice session of our courses in the lab. It is impossible. You have too many. And students access the lab when they start their thesis. So the process is that usually at the second year of the your Master of Science program, you will start thinking about this, and that if you are interested, there are a lot of other thesis offers by other colleagues. But if you are particularly interested in our work, you can send an application to myself and Professor Zanchettin. We propose thesis topics, and then if we have available seats and if there is a possibility, you will hire in the lab, and then you will start your thesis on these nice robots. This is advice. Okay.
And our last question is from Gabriele. What about a collaborative robot that helps humans search survivors through rabbits after disaster? Is it a viable operational area for a cobot despite the challenging environment awareness?
Well, I will try to answer. That's not my our main research interest, but we're surely aware of what's going on in this field as well. So there are mobile robots which are equipped with manipulators that are used in such a scenario. It's more at research level as of now, but there are some good examples of applicability of this technology. Well, challenges is not just using a cobot or not. Challenges is that you don't know what you will find in this disaster scenario, and so it's the completely unstructured scenario that you can find. So you can't do any hypothesis when you do some programming or you do something on the robot because you have never seen this scenario before. And of course, it's like Mars exploration. So you just know a little bit before actually going there. And for this reason, well, disaster scenario is a bit simpler than Mars exploration because you can teleoperate the robot because you're on Earth with both the robot and the operator, and we have reliable networks. And as of Mars, for example, there is so much delays that you cannot teleoperate the robot that is on Mars. So that has to be completely autonomous. While for disaster, you can do some teleoperation exactly as I mentioned for the surgical case, where you can have some shared autonomy. So it's not fully teleoperated, it's not fully autonomous. It's something like in the middle, where at some point the robot can take the responsibility of a certain task and fulfill that task autonomously. But yeah, the main challenge is there is the environment itself. So I'm aware of problems due to the complete the zero knowledge that I have of this scenario before you go there, and that's it's a real problem. So you don't know what to expect.
Well, thank you very much for your answers, and I think the meeting has come to an end. Thank you very much for participating, all of you, and especially thank you to the professors who were available to help us with this event.
Well, thank you for the organization. Yeah.
E vorremmo ringraziarvi particolarmente penso anche Giulio e il resto dell'associazione, quindi un secondo che si colleghino anche gli altri.
Sì, eccomi, grazie mille, è stato davvero molto interessante. Anche la linea degli argomenti, il giusto bilanciamento tra la parte tecnica e la parte un po' più diciamo, generale. Grazie mille, davvero interessantissimo.
Perfetto. Allora, grazie a voi e alla prossima.
Arrivederci, grazie.
Chiudo la registrazione. Bene, abbiamo chiuso la registrazione.